Okay, so hi everybody. So can you hear me properly?
Yes.
Okay.
Yes, it is perfect.
Okay, thank you. So hi everybody. First of all, I really wish to thank the organizers for putting together this beautiful conference and for giving me the pleasure to open it. So thank you very much for this. So as the title suggests, the goal of today is to discuss about brace blocks and in particular an explicit method to build brace blocks. We are going to see the definition in a moment. For now, let me say that this talk is based on two works, mainly the second of two works with Andrea Caranti. And these two works are generalizations of other two works of Alan Koch. And in particular, I will try to underline precisely the contributions that Alan did into the development of these methods. All right, so about the outline, we're going to start with a bit of introduction in which we define the main objects, particularly brace blocks. In the second part, we're going to jump directly into the main construction, giving some detail, but without entering too much in technicalities. And finally, in the third part, we're going to apply the construction to exhibit examples and applications, for example, concerning solutions of the Yang-Baxter equation. All right, so as introduction, I want to start from one of the main objects of interest in the last years, at least for this part of studying, which are skew braces. So a skew brace defined by Guarnieri Vendramin in 2017, building on a pioneering work of Rump, is a tripole G dot circle where the G dot and G circle are groups, and the two groups are related by a compatibility condition expressed here in the slide, where -1 denotes the inverse with respect to the first operation. So skew braces are not only interesting by their own, they are also interesting because they are connected with different topics in different areas of mathematics, like solutions of the Yang-Baxter equation, like Hopf-Galois structures, like radical rings. So in particular, when we encounter a skew brace, we have information encoded in it. And in particular, if the skew brace turns out to be a bi-skew brace, then we are in some sense the double as happy because we can find more information. Indeed, a bi-skew brace is a tripole G dot circle where whenever you choose the order of the operations, you find the skew braces. So there are two skew braces inside a bi-skew brace, maybe different, maybe not isomorphic, and so we can find more information. And what about families of bi-skew braces? And precisely in this context, there is the definition of a brace block. So let me start from G, non-empty set, and we say that a brace block on G is a family, circle I, of group operations on G, where I is an index set, such that whenever I choose two of these operations, I find a bi-skew brace on G. So we have this set, and we have this family of operations such that whenever I choose two of them, I find a bi-skew brace. So really, clearly, in principle, this kind of object can be really interesting to study because it can provide much more information. But we have naturally to ask ourselves if we can build such objects. And maybe one interesting question is that, can we build one of these objects with infinitely many distinct operations? And I'm asking this question because initially the definition of brace block was given by Koch in his second of his works, but he only worked with sequences of operations. So the index set is the natural numbers, and moreover, he starts from finite groups, finite sets. And so he is able to build brace blocks, and we are going to see how in a moment, but you can only build brace block consisting of finitely many distinct operations. So one interesting question could be, can we build a brace block with infinitely many, maybe not isomorphic, right? So the goal of the talk would be precisely to construct an explicit way to obtain brace blocks. Okay. So, sorry, I want to say that we slightly generalized the definition in our second work, which here has the letter A because it is the first in alphabetical order, precisely because we want to find, we don't want to exclude the possibility that a brace block consists of infinitely many operations. Okay. So let me jump back into the construction, and to start, I want to underline precisely what Koch did in his two papers. So in the first paper, he introduced the following construction. So he started from a finite group and from an abelian endomorphism psi of G. Abelian endomorphism means that it is an endomorphism with abelian image. So psi of G is an abelian subgroup of G. And using this abelian endomorphism psi, he was able to define a circle operation here expressed. So G circle H is G multiplied with the conjugate of H by psi of G to the -1. And he showed that the triple G dot circle, where circle is this new operation, provides a bi-skew brace. Okay, so this first construction was based on a previous work of Childs, in which he also assumed that the abelian endomorphism has no fixed point. So if psi of G is equal to G, then G needs to be equal to 1. But in that case, the skew braces that Childs built have the restriction that the two operations are isomorphic, while with this different method of Koch, the two operations need not to be isomorphic. Okay, so this is the first paper, and in the second one, he observed that if psi is an abelian endomorphism of G that give us the bi-skew brace G dot circle, where the circle operation is the one that we described before, then psi is also an abelian endomorphism with respect to the second operation, so the circle operation. This means that the construction can be iterated. So we can apply again with the construction with respect to psi and the circle operation. So we can obtain a new operation, and then we can apply the construction again, and so on and on and on. And at the end, in this way, he built a sequence of operations, circle n, where circle 0 operation is your initial dot operation, and the circle 1 operation is just the circle operation that you obtained at the beginning. And the key observation here is that the sequence of operation he found is a brace block. And he showed, moreover, that in this way, you can build brace blocks of any given finite cardinality. But again, we don't have examples right now of, in this paper, we don't have examples of infinitely many distinct operations. Okay. So these are the two main results of the two papers. And now we can try to give a first generalization of the first result. So let G dot be a group, not necessarily finite. And in the first work, we characterized all the endomorphism psi such that Koch construction and a slight variation of it provide bi-skew braces. Here you see the circle operation is precisely Koch's operation when epsilon is equal to -1, and it is something very similar but slightly different when epsilon is equal to +1. So we gave a characterization of all the endomorphisms providing bi-skew braces in these two ways. And in particular, one can assume that psi of the commutator is contained in the center, to have that the two methods provide bi-skew braces. And we also saw that this condition is really a weaker condition with respect to the abelian condition, which says that psi of the commutator is equal to 1. Okay, so we have this way to build bi-skew braces, and now one can ask, can we generalize also the second construction? So can we iterate this method to find the sequences of operations, to find brace blocks? Well, in principle, we can. So we can just replace the abelian condition on psi to obtain the weaker condition, to use the weaker condition described before. and to repeat precisely the same argument. So you iterate the construction, always taking this map psi. Yes, we can do this, but at the moment, at this point, we can observe that we never have to use really that psi is an endomorphism. So let me go back to the description of the operation. You see, psi of G is always appearing inside a conjugation. I mean, we are taking H conjugating by psi of G. We know that everything belonging to the center does not play a role when we take a conjugation, because the center is the kernel of the conjugation map. So this means that it is not really important that psi is an endomorphism. What is important is that psi is an endomorphism modulo the center. And this means that when we apply psi on a product of two elements, we find the product of the psi modulo the center. So this need not to be an equality. It is okay if it is a congruence modulo the center. So this is like the informal idea. We can assume more on our endomorphism, on our map psi. And so now let me try to give you explicitly what I mean with this. So as the setting, as the explicit setting, we start from a group, G dot, again, not necessarily finite. We denote by K a subgroup of G containing the center, and this subgroup G will K will consist precisely of the elements that do not play a role in the definition of the operation. So we have this room, we have this space in which we can throw away the elements because they do not play a role. Moreover, we define A to be a subgroup of G such that the quotient A over K is abelian. And this quotient A over K plays here precisely the role of the abelian image in the previous construction. Okay, now we consider the following ring. We consider curly A to be the ring of endomorphisms of the quotient such that the image is contained in A over K. So again, we are not taking endomorphisms of G with abelian image. We're working with endomorphisms in the quotient. And this is a ring with the usual composition as multiplication and with pointwise multiplication as addition because the image is abelian. Okay, then for all possible psi in our ring curly A, we define psi up arrow to be a lifting of psi. So this is the usual notion of lifting when you start from a map on the quotient. Indeed, it is a set theoretic map going from G to A, such that when we compute this map in G and we take the coset with respect to K, we find precisely psi applied in G in the coset Gk. So it is the usual notion. It is a map in higher level, such that when you go back with the projections, you find precisely your endomorphism on the quotients. And clearly here one can notice that we have apparently two problems. The first is that liftings are not unique. If K is different from 1, there is more than one way to have a lifting of an endomorphism. And the second problem is that a lifting need not necessarily to be an endomorphism. But we are going to see in a moment that both these two observations are not important in what we want to do. So finally, on the model of a recent paper of Caranti, we build also the set B of bilinear maps, curly B of bilinear maps going from G times G to K, such that when we compute the bilinear map, taking in one of the two components an element of K, we find the trivial map, the trivial bilinear map. So again, the idea is that K does not play a role here. Okay, so here I recall the setting. We have our subgroups K and A, such that they were K is abelian. We define these two sets, curly A and curly B. And now, for all possible pairs psi alpha in A times B, we can define a circle operation in this way. So we can take G circle psi alpha H to be the operation in which we have in the first part, the generalization of what we did before, just in this case, taking a lifting of an endomorphism, not necessarily an endomorphism. And notice that there is also the -1 in the opposite place with respect to Koch operation, but it is really the same. And then we have at the end a bilinear map, alpha G of H. And we are going to say why we also have a bilinear map in a moment. Up to now, let me say that it allows us to work also in a more general setting. Okay, so we can define these group operations, and the main theorem is that not only G dot circle operation obtained in this way is a biscube race, as happened in the first paper of Koch and also in our first paper, but we have really more, because we have that the family of all the possible operations obtained by all the possible pairs in A times B is a brace block, meaning that if you choose 2 operations obtained in this way, you always find a biscube race. Okay, so this is a way to start from your group operation G dot and obtain all these operations in one step. I mean, every operation obtained here can obtain by our construction applied with a unique application, taking a pair psi alpha, and all the possible operations that you obtain are connected between themselves in the sense that they provide a biscube race. But what about the iterative construction of before? Because up to now, we are starting from a group operation and applying just one step. So can we maybe, very much as in the second paper of Koch, repeat this construction, repeat the operation? Well, it turns out that we can. It is a bit technical because you see, in this case, this construction is based on 2 subgroups, A and K. So we have to check that when we find a first operation, then the subgroups A and K that we defined before works again in the same way with respect to the new operation. So there is a bit of computation to do, but we actually can, and explicitly we have the following theorem. So we assume the previous setting and we set the circle 0 operation to be our initial operation, and we have this theorem, which is take your sequence of elements in A times B, so psi n alpha n, where again psi n are lifting of endomorphisms and alpha n are bilinear maps. And for all possible n, we define a circle operation in an iterative way. So we start from our first operation, we apply the first construction with respect to psi 1 alpha 1, and we obtain the operation circle 1. Then we take a new pair, psi 2 alpha 2, and we apply the construction with respect to circle 1 and this new pair, and we obtain circle 2. And then we can go on and on inductively to obtain a sequence of operations, as Koch did in the second work. Then what we have in this case is that all the operations that we find are already obtainable using one step in the first construction, because for all n, we can find a pair Qn beta n in our index set A times B, such that the circle n operation can be obtained directly from the initial one using this pair, with the first method. And in particular, all these operations are already part of our brace block that we defined before. And so also this sequence of operation is a brace block, in some sense a brace sub-block with respect to the initial one. And now I want to make some observations. So the first one is that while in the Koch construction, one had to repeat the inductive definitions always with the same abelian endomorphisms, here you see we can change the pairs that we are using to define the operations. So not only with the same pair, but also something different. Moreover, Qn and beta n here have not, I've not written down the explicit description, but if you look in details at the proof, you can find the description of these two elements. In particular, Qn has a very nice formulation depending on the liftings, on the endomorphisms psi n that we use for our construction. Finally, it is the right time to say why we introduced the bilinear maps. Because when you try to apply this iterative method, you see immediately then in the inductive step, also if you start just from liftings, you find bilinear maps appearing in the shape of central commutators and product of central commutators. This means that if we want our first construction to be general enough to also include this iterative one, we really have to start from bilinear maps also. Moreover, also the liftings are necessary, and we build examples of operations obtained taking liftings that cannot be obtained just taking bilinear maps and endomorphisms alone. So really, all these parts in the definition have a sense if you want to make the construction more general as you can. Okay, that's all for the main construction. And now let me talk about examples and applications. So I've already mentioned an example in which both bilinear maps and liftings are necessary. Let me now talk about the opposite situation in which endomorphisms are already enough. So in particular, we can give a revisitation of Koch's results. For example, for the first construction, you take G to be your group, you take phi to be an abelian endomorphism of G, and then as K, you just can take one. We are working with endomorphism of G, so there is no need here to take something different. And as A, we take an abelian subgroup of G with abelian image. Sorry, we take an abelian subgroup containing the abelian image of G. For example, we can take as A phi of G itself, but we can also take something higher, something bigger to have more room to work. There is this slight detail to add. We have to work with psi, which is minus phi, because there was that -1 in the different place, but it is really something technical, not really important. And this map psi, which is the opposite of phi with respect to the addition in our ring mathcal A, which consists precisely on the endomorphism with such that the image is contained in A. Then, among all the possible information that we have in this setting, we also find that G dot circle psi is a bi-skew brace, where the operation is given in this way. So the first part is our formulation, while the second part is Koch formulation. And in this case, there is not space for bilinear maps because K is equal to 1. Therefore, the operation depends only on the endomorphisms. Okay. Moreover, we can iterate the construction using the sequence of endomorphisms psi n, where all the psi n are equal to our initial psi, which is minus phi, to obtain a brace block using the second construction. And here we can write down explicitly what the operation is. So the circle n operation can obtain in this way, so in the usual way, where Qn can be written down as a sum of powers of psi up to some corrective coefficients. Okay, and I want also to underline that, yes, in this way we are repeating the construction with the same map, but we can also do the same changing the maps. So this means that the construction that we introduce not only allows you to work in more general settings, but also to find more information in the setting we are already familiar with. Okay, if then there is a class of groups in which we can really find pleasant examples, is the group of nilpotency class 2. So start with one such of a group, so G dot, we take K to be the derived subgroup, which is contained in the center because the class of nilpotency class is 2. And as A, subgroup A, we take G. We can do this because the quotient G over the derived subgroup is abelian, clearly. And in this case, our ring of liftings of endomorphism of the quotient is precisely the endomorphisms of G over K. Now, here we want to define a map that then we are going to lift, and the map is psi n, which is the map that sends a coset in n power of the coset. Clearly, we are more than one lifting, but I don't remember if before I stated this correctly, so let me go back 1 second. When we define this operation here, we have more than one lifting, and psi, the lifting of psi is not necessarily an endomorphism, but as everything is happening inside a conjugation, it is not important if we have which lifting we choose or the fact that it is not an endomorphism, because it is an endomorphism modulo K, so which is a subgroup in the center. So when we take the conjugation, the operation that we find is just one, and it is well defined. Sorry, maybe I don't underline this properly before. So let me go back to the example in which we take as a map on the quotient the n power, and we take a lifting of this n power, which is the map that sends G into G to the n. And the fact is that while the map on the quotient is really an endomorphism because the quotient is abelian, when we take this lifting, this is not necessarily an endomorphism, for example, when the group is not abelian. Okay, but as it is a lifting, we can apply our first construction with the operation given by this endomorphism on the quotient psi n to obtain a brace block. And this brace block can be written down explicitly in this way. So the circle psi n operation is given by G dot the conjugate of H by G to the n. But using the fact that we are in a group of class 2, we can switch a bit, we can change a bit the product to obtain an equal operation, which is G dot H dot the commutator between G and H to the n. And I'm saying this because you see, the same operation here can be obtained by liftings or bilinear maps. The bilinear map is the one that sends G and H to the commutator of GH to the n. But there are explicit examples in which this map cannot be obtained by endomorphisms. So really, we are using something more. And one particularly pleasant example of this is obtained when you take the p-adic Heisenberg group. So the p-adic Heisenberg group is the group of 3 times 3 matrices, which are unimodular, so one in the diagonal and upper triangular, so 0 below the diagonal, with coefficients in ZP. You see, we are writing down this group in a compact way, so using just the 3 components of the matrix that are different from 0 and 1. But when you took this multiplication, you can observe that it is precisely the usual matrix operation that we have in this case. Okay, then what we have is that G is a topological group with the p-adic topology and the product topology of class 2. So we can apply this construction with the n power. But in this case, since we have chosen a prime p, we want to do this just for the p to the n powers. So if we take the circle operations associated to the p to the n powers, we find a brace block for G, where explicitly, when you write down 2 elements, G and H, their product is G dot H dot the commutator between G and H to the p to the n, and more explicitly, it is the usual product, and then one vector which has 0 in the first 2 components, and then an n power p to the n multiplied by this part obtained by the components of the 2 elements. And why is this example interesting? Well, the first reason is that this brace block consists of infinitely many distinct operations. You can see this because p to the n, there is this p to the n in the final vector, which means that when you change the power to p of p, you change the operation. So we have infinitely many distinct operations. But not only this, moreover, all the skew braces of the kind G dot circle psi p to the n are not isomorphic. So we find infinitely many distinct operations. We find infinitely many non-isomorphic skew braces. And moreover, and this gives an answer to a question that Cornelius Greiter asked us last year in a Omaha conference, these operations converge to the original one. So all these operations are distinct, but when you take the limit in the topology of the group, we find precisely the original operation. And this is because we have this p to the n power in the product, which goes to 0. Okay, I want also to underline that when you, if you can change a little bit this example to find also skew braces, non-isomorphic skew braces with an order of infinity more than the countable one, more than the natural numbers, because you can take, instead of the p powers, you can take the powers of taking all the p-adic integers, and so you find skew braces, a set family of skew braces with index set the p-adic number, so something which is more than countable in this way. Okay, that's all for the examples, and in the last, I guess, more or less 5 minutes, okay, I want to talk about Yang-Baxter equation and a final observation with graphs. So about the Yang-Baxter equation, I want to be very quick because yes, brace blocks, as you may expect, provide several solutions of the Yang-Baxter equation. But the way in which they do this is just the classic, the usual way of associating to skew brace a solution of the Yang-Baxter equation. So very quickly, let me recall that a set-theoretic non-degenerate solution of the Yang-Baxter equation, one of the main topics of the conference, is a pair XR, where X is a non-empty set and R is a map, here written down in components, such that the map satisfies the usual Yang-Baxter equation, where ID X is the identity on X. And moreover, we ask the solution to be non-degenerate. So we ask that the two components are bijective for all X in capital X. And one of the reasons, as I mentioned before, for which we are interested in skew braces is that they provide solutions of the Yang-Baxter equation. This is done initially by Rump with skew braces with the first operation abelian, so braces, and he obtained involutive solutions. So solution where the square is equal to the identity. And then this was generalized by Guarnieri and Vendramin for all skew braces and solutions. Explicitly associated to the skew brace G dot circle, we have a solution written down in this way. And also I want to underline that when you have a biskew brace, then you also have a new solution in which you reverse the role of the two operations. And the solution may be different and not equivalent with respect to the first one. Okay, and clearly brace blocks provide several solutions. For example, we can write down the solution we find with our method. So if G dot is a group and we assume the previous setting, then for all possible pairs, psi alpha and phi beta, the two operations obtained by these pairs give you a biskew brace. And so we find at least this solution written here. So this is the first component of the solution. This is the second one. Yes, it's a bit long solution, but it's not so bad. It seems to depend on liftings of psi, of phi, and also on the map psi minus phi. But really, as before, everything is happening inside the conjugation. So it does not care which lifting you choose. We have always the same solution. And I want also to conclude saying that this part, saying that these solutions are written down in so much generality that at the moment there are at least 4 papers in which you can find particular instances of the solutions in literature. So they are presented in a very general way. Okay, as a final part of the talk, I want to discuss about a kind of different point of view of skew braces and brace block using regular subgroups and graphs. So we start from a pointed set G1, so not necessarily a group. We write down perm G to be the group of permutations on G. And for all we say that a subgroup N of the permutation group is regular if the map that sends a permutation in the permutation computed in the pointed element 1 is a bijection. This is all well known, and you can write down N always in this way using, if you denote by nu the inverse map with respect to this bijection, you can write down N to be the set of the elements nu of G, where G runs in capital G, where nu of G is the unique permutation in N that sends 1 into G. So we can do this because the map is bijective. Okay, so regular subgroups are well known, as is well known the fact that there is a bijective correspondence between, on one side, you take operations circle on G, such that the group G circle has identity 1. On the other side, you take regular subgroups of the permutation group. How is this correspondence given? Well, if you take the circle operation, G circle H, you can deduce the elements of N just taking the left regular translations with respect to the circle operation. So N consists of the elements nu of G, where nu of G give you the left regular translation with respect to circle. So nu of G computed in H is G circle H. On the other side, if you have your subgroup N, then you can go back to this bijective map and use it to transpose the structure of N onto G. And in this way, you obtain a circle operation that it is again written down in this way. Okay, in particular, when we have two groups with the same identity, circle and diamond are the operations, and you have the two subgroups connected, which are N circle and N diamond, then by a theorem initially by Guarnieri and Vendramin, and then also generalized studied by Caranti, you have that the G circle diamond is a biskew brace if and only if the two subgroups normalize each other. So this was given by Guarnieri and Vendramin when you have a skew brace, and so you have one normalization. So again, we can see biskew braces looking at the corresponding subgroups and looking if the subgroups normalize each other. And what does it mean? This means that we can define the normalizing graph of G to be the graph which is undirected, whose vertices are regular subgroups of the permutation group, and such that two vertices are joined by an edge if and only if the two corresponding subgroups are one normalized the other. Okay, so we have this big graph. We have these vertices given by the regular subgroups. We connect them if the subgroups normalize each other. And so this means that when you have a brace block, which is again this family of group operations giving you biskew braces whenever you choose a pair of them, really give you a complete subgraph in the normalizing graph of G, because you start from a brace block, you take two of these operations, then these give you a biskew brace. And if you go looking at the normalizing subgroups, the regular subgroups corresponding to these operations, these two subgroups normalize each other. So these are connected in the graph. So really, when you have a brace block, you obtain a complete subgraph in the normalizing graph, where complete means that all possible vertices are connected. So this is kind of a different point of view to look at this story. And I want to conclude the talk with a final question, which could be, okay, we have this correspondence between graphs, regular subgroups, and skew braces, brace blocks. And can we maybe find information in both these settings exploring this correspondence? Okay, that's all. Thank you very much for your attention. And here you find a bit of bibliography for this talk. Thank you.